we're going to look at the average value of a function. Now, we want to be careful because in calculus, we've learned about the average rate of change, the average velocity. This is something different from either of those. So to do this, I'm going to start off with a sort of nice example that we can think about in order to help motivate what we're going to do. Suppose we have 6 children and we give them a bunch of candy. And I've distributed the candy here in these nice little bar graphs or histogram, whatever you want to call it. It's a histogram. But so the first child, you can see, has 8 pieces of candy. The second one has 3 pieces of candy, then 2, then 6, then 4, and then 7. Of course, the child who gets 2, child number 3, me being the third child, I know the pain of this. The third child says, hey, wait a minute, that is not fair. What we should do is we should figure out how many pieces of candy we have total and then divide it evenly among the 6 children. Well, to find out how many candies there are total, you would just add all of these numbers up and you would divide by 6. Well, we can rearrange the candy here. Let's move some candy around. We're going to kind of stack things evenly. Well, they're not stacked evenly yet. How are we doing here? Ooh, we're getting good. Awesome. Everything is stacked evenly at this point. Well, what did we just do over here? Over here, this little calculation we made was 30 divided by 6, which is 5. Now, what exactly are we trying to illustrate here? Let's go back to where we were at the beginning. At the beginning, we had this function, essentially, you could say f of 1, in a sense, was equal to 8, f of 2 was equal to 3, and so on. We wanted to find the average value of this function. Well, if you think about this, each of these squares as having area 1, the sum of those areas would be very similar to, let's say, an integral. We took the integral of our function, and that gave us the sort of the total of our function. And then what did we do? We divvied them up evenly, and we found the average value. Now, what did we do? We divided by the total length of the interval. We divided by 6. Oh, that was interesting. We divided by 6. That was the length of the interval. Well, if we're talking about lengths of intervals, we're going from A to B, and we're dividing by B minus A. Now, what did that give us? That gave us the average value. So you can see it from the picture here that the average value is the height of those rectangles. So we're going to learn a new formula here. We really kind of just presented it, that the average value of a function is 1 divided by the length of the interval multiplied by the integral of the function from A to B. And we'll use this formula to find the average values of several functions. And we'll also introduce something called the mean value theorem for integrals. So here's the average value of the function formula. The average value of a function on the interval, we denote it by f sub AVE, stands for average in case you haven't figured that out, is 1 over the length of the interval multiplied by the length of the integral, or the value of the integral. So it's really a simple formula. Let's do the first example. We want the average value of the sine of x on the interval from 0 to pi. Well, according to my formula, the average value is 1 over the length of the interval. So we're going to do pi minus 0, pi being b, 0 being a, the integral from 0 to pi of the sine of x dx. Beautiful. So we just need to find that integral. Well, we'll get 1 over pi. We're going to do the antiderivative of the sine, which is negative cosine of x, evaluated from 0 to pi. And we get 1 over pi, well, negative cosine of pi, minus negative, so it's going to be plus cosine of 0, 1 over pi times negative 1 plus, oh wait, not negative 1, excuse me, negative, or the opposite of negative 1 plus 1, so we end up with 2 over pi. That is the average value of the sine function on the interval from 0 to pi. 2 divided by pi is about 0.6366. Now I want to look at a graphical consequence of this. Here I have graphed y equals the sine of x on the interval from 0 to pi. I've also graphed the line y equals 2 over pi, which is the average value of the function. Here's the way I like to think about the average value. The average value is the horizontal line, or the height of the horizontal line, where when we take the region above the horizontal line, bounded by the horizontal line and that particular value, so here's the average value, and then we take the region bounded below that horizontal line and the function. Now my graph is a little bit off. I did this just freehand. That those two areas are equal. The average value is the height of a horizontal line where the region bounded by the curve above that horizontal line and the region bounded above that horizontal line and the curve, and the region bounded by the curve below that horizontal line, those two regions are equal when you put them when you put the two red ones together. So it's kind of a nice little consequence of the average value of the theorem, of the average value of a function. Now something else we're going to notice, we'll talk about this later. Observe, sine of x is a continuous function, and here we end up crossing, the average value ends up crossing the function. That's something we'll talk about later. For our next function, whose average value we're going to compute, we're going to look at x squared natural log of x on the interval from 1 to 5. Once again, the average value is 1 over the length of the interval, so we're going to subtract b minus a, 5 minus 1, integral from 1 to 5, x squared natural log of x dx. So we'll get 1/4 of something. Now here's the mess. X squared times the natural log of x. When I see a natural log in an integral, I tend to suspect that substitution with u equals the natural log of x might be in order. In order for that to happen, the derivative of the natural log, 1 over x that is, that has to appear, and it does not in this particular case. When substitution fails, I end up having to resort to integration by parts. That's the next most likely thing. For integration by parts, recall that one thing we choose to be u, which we differentiate, one thing we choose to be dv, which we integrate. Off the top of my head, I don't know the antiderivative of the natural log, and so what I'll do is I'll let u be the natural log of x, dv is everything else, x squared dx. du then is 1 over x dx, and v is the antiderivative of x squared, 1/3 x cubed. We put all this together, u times v, so 1/3 x cubed natural log of x. We want to evaluate that from 1 to 5, minus the integral from 1 to 5. We're going to take the product of these two things, 1/3 x cubed and 1 over x dx. Okay, so I will evaluate 1/3 x cubed natural log of x from 1 to 5, and then I'm going to have to remind myself how to evaluate that integral. I'll have the 1/4 out front. I've got 1/3 x cubed, not x cubed, what am I saying? It's 5 cubed. Natural log of 5 minus 1/3 times 1 cubed, natural log of 1. Psst, that's equal to 0. Okay, now this integral 1/3 x cubed times 1 over x. Be careful. You cannot take the antiderivatives of each of those factors. You have to simplify first. I'm going to pull the 1/3 out front. We'll have the integral from 1 to 5. X cubed times 1 over x. X's will cancel. We end up with just x squared dx. It's almost always simplifies that way when I have an integral with the natural log using integration by parts. So we continue. 1/4 5 cubed is 125. 125 over 3, natural log of 5. Now be super careful here. We're going to get 1/3 that's already there. Then we take the antiderivative of x squared, which is another 1/3 x cubed. So 1/3 times 1/3 is 1/9 x cubed, evaluated from 1 to 5. And now it's just cranking through stuff. Be careful. I am going to distribute the 1/4 to each of those terms, just for fun. We get 125 over 12, natural log of 5, minus 1/36. And now I want to evaluate x cubed at 5 and at 1. So 5 cubed minus 1 cubed. And when we simplify, we get 125 over 12, natural log of 5, minus, that's 124 over 36. Let's see, 124 over 36. Each has a common factor of 4, so that's 31 divided by 9, minus 31 over 9. That's our average value. Now, I know all of you knew that from the outset, but I figured we'd just go through all the details. Okay, so now we're ready for this mean value theorem for integrals. It says if we start off with a continuous function, the function has to be continuous on the interval from a to b. Then there is a value c in the interval so that the function value at c is equal to the average value. The function value at c is equal to the average value. In other words, now where is this little formula coming from? Well, the average value was 1 over b minus a times the integral from a to b, f of x dx. We said that's equal to f of c. If you multiply both sides by b minus a, that's where this formula comes from. What this is saying, and we saw it with our motivating example, was that there's some number, c, that's stuck inside the interval from a to b, so that when we are at height f of c, that's a y value. That's kind of like the height of a rectangle. The height of the rectangle multiplied by the width of the rectangle, that is the area of the rectangle, is equal to the function value from a to b. So we'll illustrate this in the next example. Find the average value of 10 minus 2x squared on the interval from 0 to 2. Average value is really should be one of your favorite things to do. There's not much to do. We do 1 over b minus a, 1 over 2 minus 0, integral from 0 to 2 of 10 minus 2x squared dx. I like this function. I like this function because it's easy to find the antiderivative. We'll get 1/2 of 10x minus 2/3 x cubed, evaluated from 0 to 2. And what does that become? Well, when x is equal to 2, we get 1/2 of 10 times 2 minus 2/3 of, I'm going to go ahead and compute it, 2 cubed is equal to 8. And then when x is equal to 0, 10 times 0 is 0, 0 cubed is 0, so we're done there. So if I multiply through here, we'll end up with 10 minus, I'm just doing a little cheating, 8/3. 10 is equal to 30/3, so we end up with 22 over 3. Okay, so we want to find a c. Now I should be a little bit more specific. This value c should be in the interval from 0 to 2, the interval we were looking at. We want to find the value c so that f of c is equal to the average value. Well, I know what the average value is. So f of c, we just go into and we substitute c in for x, 2 times c squared. We want this to be equal to the average value, which is equal to 22/3. Well, let's go for it. We're going to subtract 10 from both sides. Well, 10 is 30 over 3, is it not? I believe so. Minus 30 over 3. Once again, that's going to be, this is getting messy, negative 2c squared equals negative 8/3. Divide both sides by negative 2, c squared is going to be equal to 4/3, which means that c is equal to the square root of 4 over 3, which is 2 over radical 3. Let's look at the graphical consequences of this particular result. First, we have the graph of y equals 10 minus 2x squared. Next, we're going to add to this the graph of y equals 22 thirds. Well, 22 thirds is a little bit bigger than 21 thirds. 21 thirds is 7. So here is 22 thirds approximately. Now, I made this comment before that if you look at the region bounded by the curve and the average value, here's the region above the average value bounded by those two, and you look at the region below, well, the region below is going to stop about there. The area of the red region and the green region should be equal to each other, and they look approximately equal, even with my sketchy graph there. Here's the mean value theorem in action. If I look to see where those graphs intersect, they intersect right there. If we drop a line here, now here's where my calculations may be a little bit off. This value here is that 2 over radical 3. The c value in the interval from 0 to 2, for which f of c is equal to the average value. Now here is the kind of coolish thing. We can make a rectangle so that the area under that rectangle is equal to the area under the curve. So I like to imagine that this is some sort of wave, and we're going to let it rest for a little bit and watch to see what happens when it settles. When it settles, we end up with this particular area. It's the area of this rectangle. Now it's a little bit messy because the yellow and the red don't seem to want to cooperate with each other, but it's this, the area of that rectangle is equal to the area under the curve.